Hi there. My name is Jeff. Thank you very much for letting me speak to you. And I'm going to be speaking about Scala, so hopefully that's of interest to you. I'm also going to be talking about Akka. I don't know, can I have a show of hands who's using Akka here? Good, that's pretty good. And I'm also going to be talking about using functors. And again, show of hands, anybody using functors and cats? Some people. Anybody using the two together? So using Akka with functors. Just me. Okay, so as I say, I'm Jeff. I work for a company called HomeAway. I have to say that I've just got these slides back from the PR team. They've been prettifying them and stuff, so I hope they haven't messed up the formatting at all. Okay, so yes, I work for HomeAway. So to give you a little bit of context, we are a holiday company, so we provide alternative location, alternative accommodation. So anywhere that's not a hotel, and we've got 2 million properties throughout the world in 190 countries, and we're part of the Expedia family. So my job within that is, as part of the marketing technology group, is to actually take the information that we have about these properties and put them on the internet so that they're discoverable and people can come in and find them. Okay. Sorry. That's just random. Okay. Yes. So good. So this is well, my baby. These are the pages that we're actually publishing. So it's our job to make sure that we're getting the data up and that the pages are performant. To do that, we use a lot of boxes. So boxes over on the left-hand side here, this is kind of where the data is. The right-hand side is more front end. In fact, you'll actually find the top right-hand one is Node, but we try not to talk about that one too much. So as you can see, left-hand side, we're taking messages from Kafka. We then have several systems which process them using Akka, and then we're going to be storing them in Cassandra, from which they can be pulled out and splurged onto the internet. So in doing this, we've developed a reasonable amount of code. In developing this code, it's a constant struggle to actually manage the code and make sure that we're not getting too complex. It is actually something that's manageable. And so we're always looking for best practices, things that we can do, especially using Akka Streams, to actually make sure that we're organizing our code in a sensible way and not producing some horrible mess which is unmaintainable. So separation of concerns is something which we care about quite a bit. So if we think of something, an object that we might have that we're passing around, you can think of it really as being split into two parts. So a data part, so this is the data which is of interest to the business, and then metadata. So this is information which is interesting to the kind of the technical side, so tracing information, routing information, metrics, those sorts of things. If we had just a fairly simple request-based application where every request gets a response straight away, so a synchronous application, the separation of concerns probably isn't too difficult. Here we can see we've got two methods. The top method is the business concern, it's performing a very complex accounting operation. And then on the bottom we have this kind of tracking concern. So this is where we're dealing with all the metric information. We get a metrics in, then when it comes out, it's going to get stamped and then passed back as a response. In a streaming world, this is a bit different because we don't have this ability to actually use the call stack to manage our state. It goes in and it goes off somewhere else and it's gone in a thread somewhere, and that thread's probably gone to another thread. We don't really have control of that. So we end up having to pass through this contextual information. So we have, in our example here, we have Kafka messages coming in. Those messages have got our business data in them. They also have the metadata associated with that. We then have to pass those to the processing stage, which may or may not care about one or the other. And then finally, we go to the commit stage where it gets stuck into the database and various other things happen. So if we want to model that, one way would be to use a message object. So this is acting as a wrapper around our data. So we have the data on the left-hand side, the value there of some type. And then we have, in this example, we have an offset, which is a Kafka offset maybe, and tracking information. We may have other things there. And if we're actually implementing a flow in Kafka, Akka, what we're going to be doing is we're going to be defining a flow which takes a message, and in this case it's a message of type string. We're processing it by appending the word process to it. But what you can see here is that we actually have a mixture. We're exposing the value, which is our business data, and we're exposing this offset and tracking the metadata. If we want to execute this, we go from messages, we pass them via this flow, and then we pass them to the commit to be sent to the database, etc. So what we have is, again, data and metadata. So we start off with the from Kafka, data and metadata, processing, data and metadata, and commit data and metadata. So both concerns are available at any point in the flow. So we have a mix of concerns, and we also have dependencies in that things like the offset and tracking, these might be bringing in dependencies in terms of Kafka libraries, etc., etc., other parts of the code base that we don't want to expose. So, one solution to this is, I asked for a diagram of a functor. They've given me a poster of a functor. Okay, right, so what I meant was this, functors. So, for those of you who aren't familiar with functors, it's a type which contains another type. In the examples of these are list, option, and future, and it provides a map operation. So it provides a way to convert our int into another int or another type. So it's both these things put together. So we can use this with our data. So we can actually implement our message object as a functor, which allows us to then separate out. So here, inside the message object, it's dealing with the concerns of the offset and tracking, and the F in here, the A to B, that's our business concern that we're kind of injecting into the functor for processing. So if we now look at our flow again, now we can see we've got our message of type string coming in, we've got a message, and then we're just mapping the value. So we no longer have access to the metadata. We no longer have access to the offset and the tracking. So this is a bit nicer. We don't have the mix of concerns, but we still have the dependencies. So we're still dependent on a message which might be bringing in other libraries. So what we have in our flow is we have the metadata, which is external to this, before this part of the flow. In this particular part of the flow, we're only dealing with data, and then at the commit stage, we might be dealing again with the metadata. In the previous example, we were just implementing the map object directly on our class. This probably isn't the way that we'd want to do it in reality. It's much more useful to use a library like Cats or Scalzi, which will provide us a standard mechanism for implementing these, and then add some extra extra methods to our functor, so we can then do operations such as lifting, lifting. I'm not going to explain that. Right. So, back to this. So, what we have is, instead of putting the map method directly onto our message, we have a companion object. This is the single implicit in this talk. And we have an implicit type class, which is actually implementing the map for us. And what will happen is, when we use this, if we use the cats implicits, it will actually stitch together the code for us and allow us to have a map method directly on our message. So this is a bit better than our previous example, because it allows us to reuse some of the features that are already in cats. So you'd have the basic type of a functor, which has the map operation. It also has compose, which is interesting because it allows us to stick functors together to make other functors. Traverse is very useful. We've found this is one of the things that in the flows, you often end up with a list which has options in it, or some other type. You have a list of futures, and really what you want is a future of list. So using the traverse functor, that's useful for actually getting you out of that situation. So this is something else that cats are providing. Flat map might be something that you need to use, allows you to do 4 comprehensions. It's not something we've actually found a need for in our code base. And co-monad is the other one that we found useful because it allows you to pull the value from inside your functor out of the functor, which can be useful in certain situations. So the final part of this is to use a type constructor. So now we're no longer talking about our concrete message object. What we have is an abstract type f. So we have f, and we're saying that it is required that it is a functor. So the compiler needs to be able to find a type or a companion or an implementation of a functor on the companion object in order to be able to use this. But now all we're doing is we do the same map operation as we did before, but we no longer have the dependency on the message. So we have no mix of concerns, and we have no dependencies. I mentioned it earlier on, lifting. So this is something that can be useful in terms of tidying up your code. If we look at this example, you have this map, and then you have a map inside a map, and this can kind of get a little bit tedious. If we use the lifting feature, we can say that we have our process method. So this is our plain method, which is just operating on a string. We're going to create a lifted version of this. So we have our functor of whatever the f was, doesn't really matter, as long as the compiler can find one. And we're going to lift our original string to string and make it a f of string to f of string, which means that then we have 2 ways that we can use this. So instead of having the map inside a map as we have here, we can just have this map on this lifted version, which can be a little bit neater. Composing. So I mentioned earlier on that functors you can compose, you can stick functors together. So this is one other thing that we found, is that in this message, we have the data and we have 2 concerns. We have the offset, which is looking at where we are within our Kafka topic, and then we have the tracking, which might be some sort of other tracking information or metrics. So they're kind of 2 concerns that are mixed in here. What we could do is actually define them as 2 separate classes. And then what we can do is we can use the functor compose operation to stick those 2 classes together. The nice thing about this is I can have, as many of these as I want. I can choose which ones I want, and I can mix and match. So I can have the trackable inside the transaction, or the transaction inside the trackable. It doesn't matter. So then I can define my trackable and my transaction, and I can operate on it using the map operation as if it was a single thing. As far as the functor is concerned, it doesn't look like it's a thing inside a class inside a class. We're just operating on what's internally there. So our code that's consuming this doesn't need to know that we actually have several layers of stacked functors. Right, so this is probably where it goes wrong, in that I'm going to try and show you a bit of code that I've been fiddling around with. So this is something that is kind of a bit of a toy. It's when we started implementing these things, we found that it had a very nice effect on our code base in terms of separation of concerns, simplifying the flows that we had, but also then it starts to maybe open up certain other opportunities in terms of things that you could do. Okay, so this is something that I've been kind of just fiddling around with to see what I could do. So here I'm defining, again, a flow, and we're taking in a type constructor for a functor, and we have a parallelism which is just an attribute which we're going to then use later on to run the flow in slightly different modes. Okay, so this is our operation, add 1, and it's a slow operation, so it's going to sleep for a little bit, and then it's going to add 1. This then I'm converting into a future, because it's slow and we want to run these things in parallel. Okay, so now we have the flow that I'm defining, and what I have is multiple map async stages. So these are going to run the future, and when the future completes, then it will pass it on to the next stage, and the next stage, and the next stage. As you can see in the flow, we're still only talking about F. We haven't talked about any concrete implementations of the functor. So this is anything. This code isn't dependent on any of that stuff. So I still haven't made a decision as to what I want to run this thing with. Okay, so down at the bottom we have this run flow, and this is actually where I'm now saying that, okay, I don't want to run this with just, well, I can't run it with an F, I have to run it with a concrete type, and in this case, I'm going to run it with my timed functor. Okay, and so it'll start off, it'll create a list of 20 messages, and then it will run them through the flow, and then at the end of it, it's going to collect them together. Okay, so if I run my tests, hopefully this will work. Okay, so you can see that it's run several tests here. These are actually things that come with the CATS library. It'll actually provide you some tests that you can run against your functor to ensure that your functor is a well-behaved citizen. So that's a nice thing to have. Then it's run my graph spec. So it's actually run the flow with a parallelism. We can see on the right-hand side, it chose a parallelism of 2, and it's drawn me a nice graph of every time we've done a map operation. So we can now see, we can visualize data going through our flow and say that, okay, with a parallelism 2, we can see that it's queuing things up. It's going to take a little while to get through there. So maybe we want to run it again and just see what happens if we choose another parallelism. Okay, it shows a parallelism of 2 again. 1. Come on. 10. There, see, better. So 10 is looking much better than 1, definitely. So this is kind of, something that I'm kind of playing with a little bit, and I think might be useful in terms of testing our flows to be able to actually see where are the bottlenecks in what we're running and actually be able to visualize it, which is something that we've found can be a little bit difficult. Also, potentially, we could theoretically pass data from one, across the network to actually track things across the network, but we'll see what happens in that. So, in kind of conclusion, using this functor approach has had a really nice benefit on our code base. It's cleaned things up. It's allowed us to actually separate things out, and in implementing it, it actually went quite easily, which I think is a good sign that maybe we're going in the right direction. There possibly are limitations. We haven't hit them yet. In terms of the code that we're using, and there's also then possible other things that we could use this for to actually give us different insights into our code. Thank you very much.